Hey class, how you doing? Here's another video for you guys. It's problem 56 from chapter 6 homework. Some people were asking about this one. So, this is a pretty good question. I like it. What we got going on is we have this banked piece of freeway, as I show you here, or highway, and it's designed for traffic to go at a certain speed. Alright, so there's a recommended speed. That recommended speed that they're required to go really defines the angle that it's designed at. I don't know if you guys remember from the end of last class, but we discovered that you guys as engineers found that the angle needed, or the angle that you would build a road to, based on the suggested speed and the radius of curvature, both of which are given in this problem, is equal to the inverse tangent of the velocity squared over g times r, if you remember when we derived that at the end of last class. So we're given the recommended speed, v, we're given the radius of curvature, r, which you can see here in the drawing, and so you can determine what the angle that the road is actually banked at. Alright, so that's the first step, is to get that angle. Okay, once you know the angle, then you need to think about what's going to be happening in this new situation. So in this new situation, we're told that there's rain and people smartly are driving slower than the actual speed limit. So the question then is, what's going to happen or change when you're driving slower than the speed limit? Well, if you're going slower than the speed limit, that means that instead of being likely to go flying off the top edge, going shooting off over here of the road, you're actually going to be more likely to run the risk of sliding down the road in this direction because you're going slower than the recommended speed and you're still on a sloped drive. And so the interesting thing here that confuses people is that friction, if you do sum of your forces, in theory should be acting in this direction up the ramp, and we want it to be static friction because we do not want to be sliding down. Okay, and it's the maximum possible static friction. Max, there's no room there, but maximum possible static friction is acting parallel to the surface and up the ramp, preventing you from sliding down since you're going below the recommended speed. That's the first thing that confuses people. Alright, so to finish off our free body diagram, we know we got the normal force perpendicular to the surface. We know that we're going to have a weight force going straight down, and the result of these different forces will give us a net acceleration in the inward direction, which I'll draw over here because it's not part of my free body diagram. It's not attached to my car because it's a result of the other motions occurring. Okay, so we now have a free body diagram for our car. Maybe I'll pull off over here. I think I'm going to redraw my free body diagram so we can see what's going on more easily. So there's our normal force. Here's our friction force. Again, I kind of being a little more dramatic with the slope, but that's okay. We got the weight force going straight down, and we have the acceleration in towards the center. So in this case, you really have two options for your axes, and it's totally up to you. You can either define your axes as vertical and horizontal, or you can define them as perpendicular to the road and parallel to the surface of the road. And the reason you can do either in this case, it doesn't really matter, is because both of your axes options have two forces or things in each direction. So for example, if I decided to go with the perpendicular and parallel method like this, in this case now my friction is all in one direction, my normal force is all in one direction, and I would have to break my acceleration and my weight force into components. If I did it the other way, then my weight and my acceleration would be in the x and y, and my normal and friction would have to be broken down into components. So just to show you that you can break acceleration down into its components, I've chosen to go ahead and use these axes. So I'm going to call this my x-axis and this my y-axis. Alright, so with these axes now, you can see how to do some of the forces in both the x and the y direction. Thinking about how our angles work, you can observe that, as we know from previous experience, this here is our angle theta. Okay, so when we get ready to break it down into its x and y components, we can do that as well. Alright, so if we set up some of the forces in the x direction, we know they're going to be equal to m times the x component of our acceleration. And similarly, we're going to want to look at later the sum of the forces in the y direction, and now instead of it being 0, it also will be m times the x or the y component of the acceleration, because now with our new way that we're drawing our forces, right, we're going to have acceleration with a y component and with an x component. Alright, so keep that in mind and keep that straight. So what forces do we have in the x direction? Well, the way that I wrote this up here, we have the y component or the x component of our weight force going in the positive x direction, so we can call that wx, and we know from experience that that's going to be mg multiplied by the sine of the angle theta. Then we have also in the y direction, or excuse me, the x direction, but in the negative x direction, our force of friction. And that's all we have, right? So that's going to be equal to, I'm going to need to make myself some room, sorry about that. That's going to be equal to m times a in the x direction. Alright? And then similarly, for the y direction, I'll just write it down here, some of the forces in the y is going to be equal to m ay. And so now in the y direction, in the positive y direction, we have our normal force. And then in the negative y direction, we have the component of the weight. And that should all be equal to m times ay. Alright? So, at this point then, the question is, how can we go about solving? Well, now we have two equations, and currently it looks like, let's see, what do we not know? We don't know what the normal force is, and we do not know what the friction force is. More specifically, within the friction force, we don't know what the coefficient, that's what we're trying to find, right? And then the acceleration as well is unknown, but there is one thing that we do know about the acceleration. The total net acceleration is the centripetal acceleration, which is equal to v squared divided by r. So you can take this, break it down into its components, and plug it in here and here, and then you'll have two equations with just two unknowns. There's a bit of algebra involved. I'm going to leave that to you guys because this video is long enough already. Let me know if you have more questions and if you find this helpful. Have a great day.